My badge.
Thank you very much.
Okay. I know this running gag from the last time, so I had that.
Don't tell all my tricks.
Okay. Forget that. Okay. Okay. Welcome back. It's our paper still.
Very good.
Yeah. Okay, so let's get over the sleepiness after lunch and reconnect to this presentation I made this morning. So we were starting with a situation that we had the IV curve of the Shockley-Queisser limit with its specific four-color losses. And now I want to talk a little bit about how we can connect that ideal model to our real world solar cell. So normally I could talk hours and hours about that. I mean, you see the, say, very detailed end of those types of analysis you have seen in the two intermediate talks, which were giving a lot of details of loss mechanism and why something is working okay but could be improved, and you add a little bit fixed charge there and do a little bit doping there and make a heterointerface better. And all these details in some sense are important to bring this real world IV curve to something better and better and better. So that's say what I'm doing here is like a top-down approach, and I hope at some point we can meet with the bottom-up approaches of the specific technology. So there are a lot of different types of solar cells. We heard about wafer cells, silicon wafer cells, so the 3.5s are even not there. So there are other important solar cells which will be a subject of lectures during that workshop, like thin film silicon, CIGS, cadmium telluride perovskites is very important upcoming material. Electrochemical cells are really funny thing, and also organic solar cells, which by the way nowadays use different material combinations as compared to what is on this relatively old slide. Anyway, so but all the solar cells in principle work the same way. There are details that obviously are different, but the principle I've shown this morning apply to all of that stuff, because this Shockley-Queisser model is so general that you see, okay, that's say the upper limit of all these things if you put the correct numbers. We were also already talking about now coming a little bit to the understanding of specific materials and specific devices. If you're starting with semiconductor, with a conduction band, a valence band, how to get this semiconductor in a solar cell. There is one way, it's a typical PN junction, so you bend. You see that is in addition to what I had this morning. So in the morning there was everything flat, and only we had these contacts moving up and down at more or less at will, and say, okay, that's the voltage somehow, the difference between these two contacts. But what we did not discuss is that these contacts have an influence on the inside of the semiconductor, or you can have inside some assistance to that contacts, for instance, by making an PN or an NP junction. There are other possibilities, so not having only N material and P material, but the idea of having PIN or NIP structure, that's essentially not so different from that one. The only thing is that this region, which is denoted the space charge region, gets now stretched essentially over the entire device. And how can you achieve that? It's just by packing something that is not doped and not charged and not chargeable or almost not chargeable in between the N and the P, and that gives you this NIP structure. There's a doped region, there's a doped region, and that region is undoped, and then you stretch this space charge region almost all over the entire device. So there is also, say, a hypothetical possibility to make a solar cell just out of 3 different materials with different band gap energies. So that's one contact material before the metallic contact, and there is one, and that's essentially built up about, according to that idea, just have a selectivity built in such a heterostructure that the electrons cannot go out here and the holes cannot go out here. And the best thing what you can do is, I have to say, okay, that's maybe the Trump solution, it's build a wall. And that's, sorry. So you build a wall by this band offset, and then you get also a structure that could work, possibly. Okay, we will discuss this. Building a wall is maybe not a good idea, but especially in that case, it's so okay. And then if you develop things, there are a lot of choices. What you can do is you choose a semiconductor, you choose the device structure, you make a PN or a PIN or the Trump structure, and then you have to judge what is a good solution and what is a bad solution, and that's what characterization of solar cell materials and solar cell is all about. And of course, in the morning we had this very general model. There was only one quantity, it's a band gap energy, that's it. If you go to the real situation, you're getting a lot of more material parameters and device parameters that are important. And the interesting thing is, if you just go one level away from the Shockley-Quasar model, introducing real material parameters, then the minimum set of parameters you need, still on a very general level, is not 1 but 8 parameters. So there's no way out, there's no intermediate with 3 parameters, so it's not just it. And it's really exploding, as you may have got the impression from the talks this morning, how many things have to be done, how many parameters have to be measured. So that's a huge number, and I will discuss very few of them. So there is in the material characterization the 3 essential parameters that characterize, and that's for it's quite a good approximation, or it's good to know all these parameters. So that's the mobility of the charge carriers, the charge carrier lifetime, and the absorption coefficient. And all 3 of them have to be as large as possible. So the carrier lifetime is somehow limited by the radiative lifetime, because radiative lifetime and light absorption is connected. So if you have a high absorption coefficient, so a large interaction of light with your electron hole system, so always talking about the useful absorption, that making these electron hole pairs, if this is high, carrier lifetime in the radiative limit will be relatively low. So there is a limit for that one. Is there a limit for mobility? Yes, somehow. I mean, at least the carrier velocity, which is linked to the mobility, is somehow limited by relativity, for instance. It cannot be faster as the speed of light. But important is here that the mobility is not, if it's good enough, it's high enough, there's a threshold, you're fine. You're not caring about making your mobility much larger than that. And this is what we already heard also this morning, that briefly in passing, so the diffusion lengths should be larger than your device thickness. And the diffusion length is the mobility lifetime product, essentially. How fast and how long you can move, that's mobility times lifetime. And if there is an upper lifetime, which is given by the radiative lifetime, you just have to have the mobility as large that the product is good enough to give a good solar cell. And everything else is not necessary. Absorption coefficient should be high. Why? If you have a high absorption coefficient, and notably that one is spectral quantity. So there's not only one absorption coefficient, there's always the absorption coefficient for every wavelength, but the entire level should be high, because then you can make your device thinner and you relax the requirement from mu and tau. Because if you can make the device thinner because it's absorbing the same amount of light in a very thin layer, you just need not to transport your charge carriers so much. So essentially we can say there's a product mu tau in times alpha that is a figure of merit. So you can somehow replace the one by the other, at least in certain limits, and that's really the important quantities for a solar cell as a material. So then device characterization is mostly about understanding the JV characteristics, as I have outlined before. If you understand why your open circuit voltage gets lower because of surfaces, grain boundaries, or whatever, why your current density is too low, that is fine. Then it gives you a hint where you can improve, or you give up your device or improve it in a certain direction if you get a clue what this is. But that's extremely complicated. And there's why there's a lot of other, not only these, a lot of other device characterization methods that give you some detail that help you in the end to understand the JV current voltage characteristics. And then there are normal efficiency measurements, so that you determine your efficiency properly. This has also to do with the fact that your efficiency is defined under AM 1.5 spectrum, so you have to get that spectrum in your lab that you really properly measure your efficiency, and then you have these photovoltaic parameters that characterize the efficiency. That's short circuit current density, open circuit voltage, and the fill factor. So it's easy to get a high efficiency if you just measure the wrong way. So that's often, sometimes it happens. So it was, and it also gets into publications. And I'm not sure whether all the nice perovskite efficiencies that are published are really true in a margin of plus minus 50% or something like that. Anyway, so that's the basic thing about the JV curve. Again, the current density axis is negative. You have the JSC, VOC, and what you also have is a just the product of J and V over the voltage, so that's the output power, and that's the maximum power point that you where you get the maximum power out, and then you have this current density at the maximum, the voltage at the maximum power point, and the short circuit current density at the maximum power point, and the according point is then approximately there. This maximum power point, we did not talk about the fill factor up to now. The thing is, okay, this one and this one are extreme points which yield no power, but yield information on your device, which we will see later. Say very, information that's, say, relatively easy to read, to understand, at least get a feeling for, but it's not the real thing. The real thing is a maximum power point, and that's really where you try to extract power, and that's where the fill factor come in. So we define the efficiency just as a product of GSC, VOC times the fill factor, which is kind of inverse definition. So you go just the other way around and say the fill factor is the ratio between the, unfortunately not drawn here, but the maximum power you can also look at as an area at that bias point. So that's an area right here. That's just the height of this maximum power point, and you relate that area of real power to the area that you would have by multiplying JSC versus VOC. That's the definition of the maximum power point, and that's maybe the toughest part of understanding, because with very few exceptions, everything that goes wrong in your device, if it goes only slightly wrong, will end in the fill factor. You will not see much in the JSC, you will not see much in the VOC. Any bullshit that happens enters in the fill factor. Rule number 1 for device development. And that's in everything. I mean, that's really a lot of things you do not care if you're only looking at JSC or at VOC, but every tough detail, or most of the tough details, end in the fill factor. So for instance, you see it here. So that's now we're playing around with one of the material parameters in mobility. That's just a simulation. You not need to take care about that numbers. That's more an example of an organic solar cell with low, very small, thin solar cells, because organic have a high absorption coefficient, so you need not to make it thick. So you're happy with relatively low mobility. So that's orders of magnitude lower than you have in silicon and gallium arsenide or in the perovskites or in CIGS. But what I mentioned before, you can see here, that's a PIN structure, very basically simulated, just making few assumptions on band gap, absorption coefficient, mobility, and lifetime. And you see that's a very nice IV curve, high voltage, high current density, much higher than you would get in a real organic solar cell. It's just to show here what is now happening if I reduce the mobility. And you see the mobility here is reduced by order of magnitude in each step. And what you see is, okay, there is a mobility 10 to the minus 2, and you can go to 10 to the minus 3 without doing a lot. So that's a threshold. So I think 10 to the minus 2 or 10 to the minus 3 is okay. So nothing happens. So it's all the same. And there's no use to get to higher mobilities. In that case, you would not change anything. But then all of a sudden, and that's all the bullshit that enters in the fill factor, you see it, you go to the 10 to the minus 4, JSC unchanged, VOC unchanged, but the maximum power is much lower, and as GSC and VOC is unchanged, the only thing that changes is the fill factor. And then it goes rapidly down, and then you see, okay, now also I do not collect all the charge carriers from my absorber because they are so slow and they recombine too early, so I'm losing then also in JSC, in the short circuit current. I do not lose in the VOC. Why do I not lose in the VOC? For the VOC, I need not to move the charge carriers at all. I mean, there's only one charge carrier that looks what is the potential outside. Oh, it's high, I go back, and that's it. And the other side, the whole does the same. So, no need for any high mobility. The VOC is just fixed. Yeah, and then that's just a basic equation here. Mobility is velocity divided. Okay, that's the other way around. In principle, the definition should be the velocity is the mobility times the electrical field. So, and the velocity to move the charge carriers in a PIN junction. And also, you see here the term of the current density divided in two terms. One is a drift term and one is a diffusion term. By the way, that's not saying that any charge carrier that's inside the absorber knows now, oh, I'm the drift guy, I follow. And the other one saying, okay, I'm the diffusion guy running around very wildly. That's not, but it's just a mathematical separation in these two terms. So to avoid the misunderstandings here, but there is a mobility here, and hidden in the diffusion constant is also the mobility there. So that's why the current scaling with mobilities. So now for the lifetime. So the lifetime is very important, so because it quantifies the minority carrier recombination, and therefore has impact on the open circuit voltage. So we have discussed the radiative recombination already. That's not avoidable. So that's, say, the reference. The question is whether these two other guys can compete with this radiative lifetime or radiation recombination rate. Everything that's here and it's still below that one, you don't care. That's also a threshold because it cannot avoid that. But unfortunately, in practice, these two guys are there, and they are large, huge, much larger than that one in normal device. So what is it? Very simple. Auger recombination is. The question is always how you can this electron-hole pair that we have at the beginning is getting rid of the energy, because in every fundamental process energy conservation is there. So it's not just you can go down without dissipating energy, and in that scale you need to know, or this electron needs to know where I can get rid of this energy. Here it's easy. I can just give the energy back to the photon, and the photon goes away, and the electron-hole pair is gone away. Here in Auger is the drawing is maybe a bit. There is essentially an electron missing. What you have is two. In the beginning, you have two electrons. The one that wants to recombine with the hole. That's okay. There's a whole good opportunity to get back home in the valence band. But how to get rid of my energy? So I give the energy, the excess energy that I'm losing here, I give it to another electron, and that other electron goes high in the conduction band. You remember at the very beginning, these few lines stand for a lot of things. So that's only thing that's forbidden, but everything above and everything below is allowed. And this is what is happening with Auger recombination. So the second electron gets high in the conduction band, and then it's not to scale here, so it should go the same distance up, and this one goes down. And then that guy can relax in all these allowed states, back, thermalize back to the band edge and giving all the energy to the lattice in forms of phonons. So that's Auger recombination, and that's important first if you are in highly doped materials, because it's a two-particle process. You need a lot of electrons to make that efficient. So two-particle process goes with concentration square. Concentration square is small if the concentrations are small, but it's large if the concentrations are large, over proportionally large. So that's in the case of high doping. But also it's important, for instance, in silicon. Why it's important in silicon? Because silicon, this process is very slow. Silicon is an indirect semiconductor, low absorption coefficient, very long radiative lifetime. So it's in a range of hours, I think. So that's not very efficient, but that's a reference. So anything that is smaller than this very small, very slow process in silicon has an influence. And that's why Auger, even if you're not doped at all with your silicon, it's getting important. In direct undoped semiconductors, I would not say that this is a big issue. So this guy is SRH, is Shockley-Reed-Hall recombination. So that's another Shockley theory. In principle, I don't know why Shockley is first. In principle, Hall should be first because the Hall paper is before the Shockley-Reed paper. So there are two papers, and that's a few weeks earlier. So it should be Hall, Shockley-Reed, but nobody writes it like that because Shockley is so famous. Got Nobel Prize and everything. So that's, I will not go here in the detail, but the idea is first non-radiative recombination. So you get rid of the energy by generating phonons instead of a photon. And because phonons have a very low energy, you need to create a lot of phonons at the same time. So photons, that's fine, a single photon is good. But here you need a lot of phonons. It's like 50, 60, 70, depending on your material, the average phonon energy. So, and that's a very unlikely process if you make it in one step. If you have a state in between where electron can go to a defect state, and this is why our colleagues from the gallium arsenide and the silicon are so much worried about defects. That's a defect is something that puts an allowed state into the forbidden area. And that's why is this efficient in recombination. It's because the electron then can sit on that point or go there first before doing the next step, so make a little pause in between. That implies that, okay, in the first step you need less phonons, and in the second step you need also less phonons always at the same time. You share this big amount of phonons in two portions, and that makes this probability of this effect. That's, I think it's going somehow with the faculty of that, so it's really a very big impact if you divide that into two or even into three intermediate steps. So it's getting much more efficient, and that's what Shockley, Hall, Shockley, and Reed describe in their papers. Both worth reading because the approach is slightly different. So it's worth to look at both perspectives, but not that much complicated how it's described. But it's a bit involved mathematics, so I'm not after lunch. I'm not doing that. You can come to my lecture in Aachen and you can. Okay. So the last one is the absorption coefficient, and we have this seen that before. That's or similar graph is just for a bunch of materials, and you see it's a spectral quantity. It depends on the photon energy, so you get an absorption coefficient. The unit is should be alpha here. I don't know why this turned into a 1/centimeter. So the inverse quantity would be absorption length. So you can compare that to the thickness of a device. And you see a lot of materials, copper indium selenide, copper indium sulfide, gallium arsenide. They have a very steep rise of this absorption coefficient, and this because they are direct semiconductors. So in contrast, crystalline silicon, and then there somewhere is the bandgap energy. Crystalline silicon has very different shape, and that's because of being a direct semiconductor to get indirect semiconductor. So it's very bad in absorbing light, but still has a lot of advantages. But what you can see is, okay, if I want to have absorb almost all light starting from the bandgap energy, so you remember in Shockley-Queisser model that was just a step function, and translated into the absorption coefficient, that would mean that just jumps from 0 to infinity. So infinite absorption coefficient also means that you need no thickness at all. And by the way, in principle, the Shockley-Queisser model solar cell has no thickness at all. It's all is in principle theory about areas. There is no third dimension in the Shockley-Queisser model, which is, by the way, also interesting feature, but I will not talk about that. So, okay, so you have, so they say it's almost a step function, and you can just see, okay, if I want to get within few tens of milli electron volts getting to such a value, you see, okay, so for copper indium selenide, a thickness of 1 micrometer, 10 to the minus 4 centimeters would be fine to have a good solar cell that is almost as good as a step function for that range. And that's the same for all. Gallium arsenide is slightly different. That's why you maybe need a little bit more than a micrometer, but with indium phosphide and everything else, you can you're very fine with even less than a micrometer. In contrast, for crystalline silicon, okay, so that's really, if you just have a thickness of 1 micrometer, you see you lose a lot. You lose almost everything here in between that range. So your open circuit voltage, your recombination is made by that energy. J naught would be high because that energy is relatively low. JSC would be very small because this would somehow correspond to much higher energy. So because the absorption coefficient is so low, so what you do is you go to thicker devices to bring that point closer to the band edge, and so it's why the typical crystalline silicon solar cell is in around 100-200 micrometer thick, and as you can see just from here. That's and then you have the amorphous silicon, which is somehow something in between, which I would not discuss too much. So that's the important material parameters. So about the doping, yeah. So I was encouraged to bring in more discussions because to wake you up and wake myself up. So so get into the mood. I will ask questions shortly. Okay, no question here. That's just another material property that we were talking about this equilibrium Fermi level between the conduction and the valence band. So this defines the number of charge carriers. Is all this, say, textbook knowledge about semiconductor physics. You can do the doping and shift the equilibrium concentrations of electrons and holes forth and back. The interesting thing is that the product of these equilibrium concentrations remains the same, and that's important also for calculation. That's only depending on the band gap energy and the density of states in the conduction and in the valence band. The important thing here is that in some materials we can have a p-type and n-type doping, and that enables us to make PN homojunction solar cells, for instance in silicon, gallium arsenide, but in others we cannot do it. So it's not straightforward for every semiconductor to be n-type and p-type doped by adding a few ingredients. So that's kind of a problem, but that can be worked around. So now going back to the device geometry. That's just putting some of the numbers here to this band diagram. Now you see that really the third dimension really gets important. This dimension, that's still the energy axis. Here now we have the spatial coordinate. That's now getting important, and that's just the important quantities are going along with a PN junction. So the built-in field. So it's the difference between the conduction band position here and on the other side, and the same for the valence band positions here and the other side is made by this built-in potential. That's amount of band bending you have, and okay, you see also you can manipulate this by controlling the doping or the difference between the Fermi level here and the conduction band here, and the difference between the Fermi level here and the valence band there. So if you make that smaller, these two, immediately your built-in voltage will increase, and that's just here expressed by this equation. Okay, this morning, if you remember, so what is this situation? So now I start to ask questions. So I just run around a little bit and look who is sleeping. And so no, I'm not doing that. But maybe I would be. So what was the weak point about just looking at that situation as I have discussed this morning? Pardon? The separation, that was the issue, but that's we're doing not so bad already, because there is if I have an electron hole here, holes like to go up like the bubbles in the mineral water, so it would not like to have to go in that direction. So for the hole, it's more likely to get out there, so that's fine. For the electron, okay, there is no barrier there, so that's an issue we come back in a few minutes. But if it's just running around by diffusion here, there's no electric field. But if it's getting into that region, so it's just going away. That's a good point, but that's not the point I wanted to hear at the moment. So if you look at these two metal contacts, what is the situation? Again? Exactly. So Fermi level is aligned. That's so there's no voltage. So still we're in the short circuit situation. So that's the point here. So that's everything fine. You can separate charge carriers, maybe not as perfect as we would to wish, that's a good point, but still it's kind of okay, but that's not the situation we're talking about. The situation we're talking about is that one. So now these two are different. Then I have a voltage, and if I still separate the charge carriers, then I'm getting a power out. And the point here is, okay, you have this external voltage, so we have now two Fermi levels, one for the electrons and for the holes. I did not explain this too much detail in this morning. And still, okay, so we reduce the built-in voltage by the external voltage. That's now, because the point is, if you have here two metal plates, that's your contact where you end up. And between these metal plates, there is a voltage that was not there before. Is somebody from electrical engineering? So, what do I need to build up a voltage?
You need a carrier on both sides, and you have a difference between the thermal.
Yeah, that's what I ask something that's coming from pure electrotechnics. If I have a voltage, what do I need to build up a voltage? Charges, exactly. And that's a capacitor. That's not maybe not the nearest thing you think about. And, there's a saying that if a professor asks students, the relaxation time of students is 3 minutes. So no, that's experimentally proven that 3 minutes is the time you need to get rid of the shock. So don't be ashamed if you're not fast enough. I'm mostly also not fast enough. So anyway, so you have a capacitor, and the capacitor is really hidden there in the space charge region, because you make the space charge region smaller. And how do you do that? By just removing charges from the space charge region. That's a capacitor that is used to build up, or is there to enable that you have that voltage difference. In between these two plates, somewhere you have to accommodate these charges or withdraw these charges. Okay, that's one lesson. Always search for the capacitor in your solar cell. That's always a good idea. Now we can remember this morning. So what about the electrons that we withdraw and inject? And if you look at that situation, very similar to what we discussed this morning, and we can put a very similar equation now only for the electrons, and we can put the same or similar equation for the holes. So going from left to the right, I have to overcome this potential barrier. But this is already smaller because here we have applied voltage. So the barrier here is smaller, and that's combining these two terms. And the other way is if you have more electrons inside here, then you have an equilibrium. There will be a component in the other direction. And again, that's two components. That's not implying that one electron knows, oh, I experienced a photon and coming from the valence band and now getting around and have to do all the work and bullshit. I don't like that. And the other one is, oh, I'm getting inside and getting into a photon and get the eternal life in space or something else. That's not the case. That's just a mathematical construct which is instructive, that you have one component that's going from the inside to the outside and one component, and you can control that by these two quantities. So what we have learned is that really now we have a realization of a contact which we on a very general level discussed this morning. Now we see, okay, that's realized by a PN junction. And the same is true for the holes as well, and you sum it up and then that's it. So now getting to the PIN, so again we are in equilibrium. Now look what is happening at applied voltage. Okay, we see again a built-in potential, now it's going from left to the right, is reduced by the external voltage, so that's what is happening. Question, I do not wait for 3 minutes, maybe somebody is faster. What does this mean for an electron and for a hole here if we have this reduction of the built-in field by a bias? They move, yeah. I mean, they move preferentially in the direction of the field, so the electrons move way up. So they can also, because of diffusion, both is there, so they can also go uphill. We have that but mostly will go downhill, especially if the mobility is low. So this is why in few of technologies you prefer to have PIN junctions instead of PN junctions, because your mobility is so low that you not only want to rely on diffusion, but you need a little help from the field, I would say. And that's given by, this is why you make the space charge region so large, almost the entire solar cell, and then every electron very slowly moving, at least knows in which direction, instantaneously knows in which direction to go, and has not to diffuse around to check the one boundary and check the other and find out that on that contact I can get out more easily than on the others. That was a PN. Here is immediately more or less clear. So, but what happens here then if we have, say, a little help from that field? Done? Yeah, recombination will happen faster because you have more electrons and holes at the same time. But just looking at the field, it's getting smaller, implicitly. So that's really the power of this built-in field is reduced with your working condition. So that's a critical point in this PIN. If you really rely on the EI effect and the field effect, so it's getting weaker and weaker the closer you come to your working condition. And that's one limitation of PIN junctions. Okay, so again we can have this equilibrium between all this interplay. So I have only, instead of a double line, I have one force and back. To make things a little bit easier, you have also to know that this arrow does not exist in your device, so it's not interfering with the movement of the electron. Anyway, so
Uwe, I have a question.
Yeah.
So the built-in potential is a static field.
Yeah.
And how can a static field produce work?
Actually, it does not produce work. No, that's not the point. That's the point is that it's an enabler to transfer. I mean, the work. Now getting very fundamental, because I have conducted this discussion so many times and with really tough partners, and that's one of the tough experience. The point is the work is produced inside. The engine of that, say, vehicle is a generation and as a counterpart, the recombination inside the absorber material. All what we do in device engineering is not building the engine, we build the gear. The engine is just producing power, but totally senseless power, because I mean, if you remove your engine from your car, put it on the street, the engine will not move forward. We can try this out if you like. But what you need is a gear, and all the field thing stuff is nothing else than optimizing the transfer of the internally generated free energy with as few losses as possible. And here, so it's an enabler, it's a gear. And that's also true for low mobility semiconductor, where you can just prove by numerical simulation that it's much better to have this PIN if you go down with the mobility. But it's not saying that the field producing any work. It just allows the work to get outside. That's, I think that's very, very, very important thing. Now looking at this force and back of the electrons, and now the equation here has slightly changed, and I find this quite interesting without going into the detail. But what is behind this equation is that, okay, the recombination mainly takes place, or in the average takes place, in the middle of the device. And now if I look at the electron current, it has only go half of the barrier. So that's why here I have to divide the built-in field by 2, and also the action of the applied voltage by 2. And of course you have the similar equation for the holes, but in that case I do not add up, because they are connected in series. So both are valid, and the same current has. And that's one way of introducing ideality factor in the diode equation. That's essentially a diode equation, and you see this 2 is just a correction factor to the classical diode equation, and that's valid in PIN junctions. Okay, now possibility 3, and that's the question: what is happening with the built-in field? If there is none, but you apply a voltage, then you get the situation. And now, so the built-in field in the end is negative. It's just everything that you get as a voltage adds as a barrier to get the electrons out of this. It's still possible if the electrons are very, very mobile, and mobile enough to have thousands of atoms to get. They cannot get out here. That's a benefit of the wall. And then finally they get out. The other thing is, okay, for the injection, that's still always the same barrier, so that's not modified. So it's quite interesting situation, but it's not really robust in the sense that if you have a little bit low mobility, little bit low lifetime, this will not work. What will work instead is if you combine, so best of the two worlds, having a PIN junction or a PN junction, and then that was your point with the electron going out on the wrong side, which really is that's because that's the reason behind why switching from the full area, for instance, full area metal contacts in silicon, to the PERC technology, because you want not to have metal on the backside of your of your silicon solar cell, and that's true for any solar cell. At a certain level, you need to take care about the backside, and that would be building the wall at the backside, so that the electron only have the chance to get out. That's surface passivation, if you like, or high selectivity, so the electrons cannot go out. They go out here, and the same for the hole. But still you have this PN or the PIN structure. That's the way how you can optimize things. Yeah?
In the previous slide, where is the SC?
Pardon?
In the previous slide, not this one, but before, where is the SC?
The?
Potential at zero current.
In that one or in that one?
Here.
Some, yeah, so that could be VOC. I'm not very specific about that, so it depends on the, in that situation you had a certain current, and if your generation current just matches that one, you would be in VOC. I mean, VOC would more or less look like that. I mean, okay, that's in that case, okay, VOC would be the situation. It could look like that, and the situation would be that your, I mean, you see it here. It should be zero. That can be zero because that's zero and that's 1. So 1 minus 1 is 0. But it can also be 0 if that one equals that one and both are large. And if your concentration inside n divided by n0 just is the same as that one, you would be on VOC. So then both components would be equal. The net effect would be 0. So you can actually really see VOC in that equation. Okay. So I have to hurry up. So when I should finish in half an hour? Like
Half an hour.
half an hour. Okay. So let's get a little bit to the current voltage curve and the explanation. We were talking about these 3 situations. You can somehow imagine that as like heating a teapot in different bias conditions. So one bias condition, you leave everything open, so water is boiling and the steam is coming out, and you count just the amount of steam that easily comes out of the teapot. So if you close that door, that would be the VOC situation, and heat, then the thing maybe explodes, so don't try that at home. But essentially what will happen, you will find the weak spots where the steam can come out without going through the main exit of the teapot. So that's VOC is showing you the weak spots in your solar cell. That's what is meant here, and at the maximum power point you just really are somewhere in between, and you're not closing that down. So try to generate as much power by the steam that's coming out of your teapot. That's the maximum power situation. I'm going a little bit over that. So to summarize here, it's all about now a bit more with equations and with the currents. You have seen this equation before, and it's possible just to divide that into 2 parts. That one is here, that's a current that is essentially recombination. Is recombination. So that has diode form with an ideality factor. If you like, you can also interpret this ideality factor as a voltage dependent of your J naught, but that's not important for the moment. So that's the recombination current, and the photocurrent now is JSC times Q, and you have this seen before integrated over the sun, but we went from E gap to infinity without that term, implicitly saying, okay, my external quantum efficiency, which is here, is just making this step function from 0 to 1, and then you can omit that and just replace it by the boundary, by the integration limits. But in real device, you have this external quantum efficiency, and if you integrate it up over the solar spectrum, that gives you your short circuit current. So talking a little bit about the quantum efficiency, so I'm not having that defined before, but very easy, the external, yeah?
Can you go back to this slide? It's maybe that when you say the -1 should be outside the external solid.
Pardon?
You have the exponential, yes.
Ah, okay, yeah, right. Okay, yeah, it's always the same. So we, yeah.
Maybe
Yeah, okay, so rule number 2 for today, if you're writing down the diode equation without using two brackets, two types of brackets, that's most likely wrong.
you did it on purpose.
Huh?
You did it on purpose.
Yeah, that's wrong here everywhere. Yeah. That's thank you. Yeah, that's quite important. Just I can excuse myself by saying I did not make this transparency. I don't tell who was making that. No, I'm quite aware because yesterday evening I did some of the slides you have seen this morning, and I had at least 3 times the effect. Damn, I forgot the second brackets. And, okay. Anyway, okay. So what is the external quantum efficiency? The spectral quantity again, like the absorptance, is something between 0 and 1, and is defined just as a number of electrons or electron hole pairs that you measure at this terminal of your device per incident photon. As in the Shockley-Queisser limit, we're still assuming that there cannot be more than 1 electron hole pair per photon, so the external quantum efficiency can only be unity in the best case, but in most cases will be lower, and you just measure it by measuring the short circuit current and the incident light intensity. That's not that easy as it sounds to make that quantitatively, and then this gets you the external quantum efficiency, and you can also then from that derive the internal quantum efficiency, which is nice to have, but for our purpose at the moment not so important. This is one of the slides you have really in your file, so I don't just say, okay, there are different ways to measure quantum efficiency using white light, then a monochromator, and then you change the color of the light and always measure essentially the current of your solar cell. But for the sake of time, I would skip that, so you can find that in the file, and also there is this description of the method how to make it with different reference and monitor cells, make it sure that it's quantitatively correct, because that's a very, very important measurement for the solar cell. So a brief detour, which I found important also because we have discussed, or we have seen similar things in the talks this morning. So what is PN junction? We have already discussed that there is a PN and there's a space charge region, and you have this built-in, or this band bending in between. You have these charges which makes a capacitor. But now we have seen several times that willingly or unwillingly, or you're making not one, you cannot, or you make not a p-n junction by indiffusion, but you make a junction by bringing something on top of something else. For instance, a contact layer on your absorber layer, the indium gallium phosphor indium antimonide to the gallium indium stuff, and and then you make it lattice matched, and you get everything and get 50,000% efficiency or something like that. Yeah, not just a picture that I had in my file. I think it's just taking away the horror from complication. If you understand that one, you can also understand that one if you have a P and an N which are made of different materials with different band gap energies. So you have the situation, different band gaps, different Fermi level positions, and what you do. This is shifted, this EC should be here, this EF should be here. If you bring it together, you preserve these differences that make then the band discontinuities, so band going up and down, or both going up, so depending on everything. That's seen here. But at the same time, you need to equilibrate the Fermi levels of both systems. And that's happening by just then bending things around, that in the end, this Fermi level, which is here in different energy positions, getting flat, and then it's all the same as in the p-n junction. You get a plus space charge here, the minus space charge here. You can control the built-in voltage in the similar time by the doping of both ends. So that's not very much more complicated than just the p-n junction. And it's an important option if you, for instance, come up with absorber material that you cannot dope. How can you make these selective junctions we were talking about? You just have, if you have a, say, p-type absorber, you need to have an n-type partner. A good idea to have something like that. And that's, say, one example that's getting more complicated because three materials are on top of each other, and one is maybe in the middle of the space charge region. That's just to make a little bit, not take it too serious. I mean, but we did not ask you about the meaning of one of this and how you can calculate that one. But still, that is just okay, and that's the zinc oxide, cadmium sulfide, copper, indium, gallium side, and it's not clear whether there is really that cliff here that the cadmium sulfide goes up. It's sometimes people do it like just that. If it would go flat here, you wouldn't even notice that you go from one material to another. So that's sometimes only for it's small, or it's even a little bit negative. So it's not really critical here. So the interesting thing is, okay, why you need 3 layers? So that's say the zinc oxide is very highly doped, so it's also big, large band gap energy. So it's transparent, and it's attracting electrons. So electrons going from here to there, and hopefully hopping over that, or in fact hopping over that barrier if there is really a barrier. So that's fine. So it would be sufficient to have a zinc oxide on a copper indium gallium selenide. Everything would be okay. But that's something that we often have in also in tomorrow you will see in the heterojunction solar cell you have the same thing. There's always often a very thin layer in between that helps, let's say, there are multiple functions. One is, say, okay, maybe that's passivating the surface here. So it's, say, better to the CIGS surface to put cadmium sulfide instead of zinc oxide immediately. It's also keeping away the holes from going there, maybe somehow recombining with the electrons here. So this kind of passivation, magic passivation layers is almost a standard, I would say, in most of heterojunction devices that you have such a thing, and only the combination of two materials works quite well in collecting charge carriers and passivation. I put this also on that, and then now I come back to the quantum efficiency analysis, because that's a quantum efficiency of a CIGS solar cell, and you see all these different components, quantum efficiency, external quantum efficiency. So, and you see all the important features that are in this structures. You see, first of all, okay, that's white is are the used photons at different wavelengths. Everything else are losses. So what you would like to have, of course, is something that is, so that's wavelength, so just inverse to energy. Shockley visor would be unity here and dropping somewhere here to 0. And yeah, and you somehow see, that's a pity. I mean, that's a lot compared to the step function that you lose, and you have to understand, and that's really you need also a little bit numerical work to understand what is going on, and you can attribute all these missing areas to these different mechanisms. So, for instance, if you go back here, is a wide gap zinc oxide. That's a wide gap material, but still there is a gap, and that will, some of the high energy photons that come here will be absorbed in that layer, and that's why in the ultraviolet range there is no quantum efficiency, because just the light is absorbed in the zinc oxide, and that's principal recombination, because just you're making electron hole pairs, but they're not surviving for long, and they just go. Then you have also the zinc oxide free carriers. That's a recombination mechanism, or the energy loss mechanism that I did not discuss earlier, so I leave that out. It's just saying, okay, free carriers take away photons without doing any good. So that's a loss. Then we have again the recombination in the cat sulfide, so still that one is also not giving a lot of electron hole pairs that can be used. So that's D, and then a lot of other things. And interesting thing is here that there is, if you add everything up, there's still 2% missing. So you can ask yourself what is going on there. And at that time, and that's almost 20 years ago, say, okay, maybe there's just inactive area. There's nothing. I mean, that's a thin film solar cell. You wouldn't notice if some small spots are just missing. In fact, that's true that a lot of thin film solar cells have just that area in a very small scale, not easy to detect, that just does not contribute. And then it's interface recombination, and that's because any electron that comes from the absorber must go over that interface, and if there is a certain probability to recombine at that point, just regardless where from this electron comes, with regardless from which energy photon it has been made, it's just not there. Nowadays I would rename this as a lack of interface selectivity. So that's a selectivity loss. Anyway, so that's what you can do and what you can learn. And then you can make all this kind of analysis on it.
What is incomplete absorption? The last one.
Okay, that's incomplete absorption is, okay, that's where so that's somewhere here is a bandage of the, and that's the region where your absorption coefficient then sharply drops to very low value. And this implies that, okay, if the photon is gone through the absorber, it's only 50% of the photons are maybe absorbed in the first run. And then, in principle, it's a bit less. You can do a little bit more analysis on that and say, okay, what is happening if it's going to the backside? Is it coming back, so getting a second chance? Is there light trapping? I think we will have this issue. That's all in this incomplete absorption. So that's absorption that is not a part of this absorption that's not in the CIGS making electron hole pairs. It's in the metal, for instance, where it's just gone away. So that's meant with that one. And also, even if it's reflected, if the photon comes out again to the front, it's also in that loss. So that's band edge losses or whatever you would say. Whereas here CIGS recombination means, okay, we make electron hole pairs with high probability. So I have to subtract that one and that one. Then, okay, the electron hole pair does not make it to the contacts. That's in that area here. But here we even do not make an electron hole pair anymore. I mean, in principle, you can say everything below is incomplete, but somewhere you have to stop your analysis. So. Okay, good. And then you can look at all the contributions from what you could get at a given band gap energy and where you lose it at which point of the layers and so on. So now for the last 15 minutes, having passed the short circuit current, now going to the open circuit voltage. Very briefly, open circuit voltage, as you see in the teapot picture, is about recombination. So there is nothing, photons going in, but no electron hole pairs coming out. So they have to recombine in the one or the other way. And that's why the VOC, or the open circuit voltage, is probing your recombination in the device. And so that's some general statement. Okay, mostly non-radiative recombination is dominant, and single current voltage curve says nothing. But you have to use your fantasy because you cannot really observe the electrons and holes, what they are doing. So there's no microscope to look at them. And so you need a lot of experience, a lot of simulations, and a lot of experiments as well. So briefly, we were talking about, and that's even in a radiative recombination, in the Shockley-Weiser we have assumed that the absorptance has a step function, and the emission spectrum will calculate from this step function according to the equations we had before, looks like that. So that's essentially rising at the band gap energy, and then you have Boltzmann tail or Maxwell tail here for the higher energy, because these electrons have a certain temperature. So that's your emission, your loss in the Shockley-Weiser limit, or okay, in an almost step function here. That's not really a step function. What we have here is now saying, okay, maybe we have fluctuations of the band gap energy is not the same all over the same entire absorber material. You have, for instance, CIGS, you had at some places more gallium, less indium, and the other way around. So band gap is not only a single band gap, but many band gaps, and can model this by having a band gap distribution. So that's the width of the band gap, maybe 50 millivolts plus minus. And then you look at how your absorption edge looks like, and it's not very much of a step function. Even that is not a step function because there's a small scatter assumed in the band gap energies. But it's pretty close to the step function. But that's quite different. So it's the absorptance is different, but also your emission is different. Now it's getting, because absorption is smeared out, also the emission gets broader. it's also shifting to lower photon energy, and it's much more emission. So if you take the integral or the integral over that emission peak and that one, you see that that one is much larger than the other one. So that's a small modification to the Shockley-Queisser approach, still radiative, but just assuming not a single band gap, but a little bit disorder in the material. And you see your loss gets much larger as compared to the band gap, average band gap still unchanged. Just because of the disorder, you're getting more losses. So, but now going to the non-radiative recombination mechanisms very, very briefly. Again here a sketch of for case of CIGS. What you have here is different locations where you can have the recombination at the interface, in the space charge region, in the neutral bulk, and essentially also at the back. So that's a big question in CIGS research. So is there molybdenum selenide forming, and is it maybe as beneficial as here, that you have a small, at least a small band offset that prevents the electrons from falling into the metal. So that would be a loss. If there's a band offset, it would mitigate a little bit, but as we know by now, it's not really the nice thing from the 3.5s where you can really tune the thing up. So still the back interface is kind of bad in CIGS, and people are working with passivation schemes to get better here. So that's for the back recombination. Then we briefly walk through the recombination currents. In principle, what you're doing is all recombination. You just all is in parallel. You're just integrating everything, everything up. And there is a simplified equation for the Shockley-Ritter recombination rate. That's radiative recombination. So everything contributes, but the question is what is dominant. So that gives you some of the basic equations for neutral bulk recombination. So that's outside the space charge region, and here is assumed that okay, that's a neutral region, but it's also the region where you have way more holes as compared to electrons. And I think due to the lack of time, I would not go so, and also it's a bit late in the talk to discuss all the equations. But just from all that, you see the diffusion length plays a role. That's the diffusion length. This is a lifetime. It's the diffusion constant. So, but the basic thing is, okay, we have, this thing has this form that we have what we had earlier as a barrier or activation energy is here, the band gap energy, and we have also discussed the ideality factor, which is unity, at least in the ideal case, if you can calculate that. So that's, keep in mind, there's an activation energy, that's the band gap energy, and the ideality factor is 1. And now I'm happy that I discussed the PIN stuff already before, and we found out that in this PIN, if you have the recombination just in the middle, you're ending up with something like an ideality factor 2. And also you have seen that the barrier is halved in that equation, so the activation energy in that case would be just half of the band gap energies, and that's not needed to go through those equations. But if you like, you can recalculate, and under this assumption you get this result. So we have half of the band gap energy, ideality factor of 2, and now coming to the interface recombination here. And here the interesting thing is that your activation energy is not more the band gap energy of the absorber material, but the barrier height at that interface. So that's the barrier the holes have to overcome to get to that interface. That's essentially this activation energy, and the ideality factor can be, or is in that approach, again, unity. So that gives a little bit an overview on what you can get out of the ideality factors. So we have Shockley's diode theory, neutral bulk recombination gives ideality factor 1, recombination in space charge region. If you do it a bit more in detail, you can get anything between 1 and 2 for space charge recombination. Interface related recombination ideality factor is 1. So with the ideality factor that you can measure, you can distinguish different, at least different groups of recombination mechanisms. There's a sharp line, and if you're getting to ideality factors larger than 2, that's more tricky. It's not been made by that one, and there are different more sophisticated. So if tunneling is somehow involved, here you see always tunneling, or the material is very inhomogeneous, you can have ideality factors larger than 2, but that in most cases that's a very bad device anyway. And the activation energy, just let's look at that point, is important, because if you see the activation energy is my band gap energy, you note that the critical point is still somehow in your absorber. So interfaces are doing reasonably well. And only if your activation energy is getting smaller than the band gap energy, then you say, okay, that cannot be my bulk, that must be an interface, very roughly. And one way to measure such a thing is just very simple. You just measure the VOC at a constant JSC, but as a function of temperature. And what you then see that, okay, there is a temperature-dependent decrease of my VOCs. The lower the higher the temperature, the lower is my VOC, but the lower the temperature, the higher is the VOC. And then you look at that curve and extrapolate it to T equal to 0. You normally would not measure that point because it's much too expensive to get to 0 K, and it will not work anyway. But you can extrapolate just, and then you see, okay, that's would be my activation energy, and that gives you some information. So I have 1 minute now for the toughest point of my presentation. So I would just skip this. Okay, here you see the proper picture of the fill factor, and essentially what is also in your files is one nice method to measure explain fill factor losses with respect to an ideal situation, and distinguish between fill factor losses that come from non-ideal diode behavior. So that's non-ideality. If this is larger than 1, your fill factor automatically gets smaller. But if you have a series resistance, also will affect the fill factor. And that's a very nice method to distinguish between these different contributions. So it helps in one of these cases to see where you're losing your fill factor. And that's, I think that's all about that method. So you just look at the papers, and I give you, somehow we did not get a very good PDF. So that's the list I have shown you at the very beginning. So it's more than half a day away. So that's our five assumptions. And if these assumptions are violated to the worse, you can ascribe this to somehow a certain sort of a loss and give a certain figure of merit, and that's what in the paper, and that's really my last slide. And that's, I think, again, give me a minute more to walk you through the set. Because what we have taken here is really at that last year, all the record solar cells from all these different technologies. And we can, I mean, that's not, if you have the data, and that's essentially you need the IV data for doing that, but it's quite instructive. So we have these four arrows that you have seen before are associated to four different figure of merit. So you see that each figure, so that's a bit tricky. Actually, that we did invent that plot. I think I've never seen that before, something that is semi-logarithmic, but starting from unity and going down. So that's, I mean, we could not convince Origin to do it somehow automatically, so we had really hard time to but the nice thing is, because of the logarithmic scale, and I have to say, okay, the efficiency is a product of JSC, VOC, and fill factor. And so the losses are also products. So, but if you have products, you cannot add them up. But you can add them up if you choosing the logarithmic scale. So regardless how you place those blocks is always correct. So the size is really the size of the loss. And then we have four different losses. That's just the figure of merit short circuit current. That's the short circuit current that you're losing in your actual device with respect to the same shock liquizer device. So that's something that's smaller than unity as a factor, and that's why it's negative here, going from 1 to, as on the log scale is going down. Then the same thing is what you have in your real open circuit voltage related to your shock liquizer open circuit voltage. The only thing which is a bit critical to find is really to have the right proper band gap energy. That's the same definition for all these different materials, but then you can do it relatively easy. Then derived from that one, there is this small blue thing that's just a consequence of these differences. So if you change VOC, you also change the fill factor. That's why we're having the blue. And then you have the fill factor losses, which then have mostly somehow come from resistive properties. So that's very simple, but it's instructive to see what these record devices do have, and you see that okay, the gallium arsenide, as we have seen this morning, is the best, and you see really that guy is at the limit. So there is still a little bit scope for the short circuit current. So Andrea, you hear me? Yes, that's what you have to do next week. Make that smaller, please. But you see, then everything here, there's almost no loss between the VOC and the VOC shock liquizer. So that's really at the radiative limit and has at the same time very steep, sharp band edge. So that's, and also almost no resistive losses here. in the crystalline silicon, you see, okay, everything is even the JSE is better. Yeah, you have to catch up with the silicon. So that's somehow that's still to get here would help there. So the JSE is not a problem for the silicon. Is also light trapping is very, very important, and that's and that they're doing really, really well with the silicon. So there's not a lot of things, but that green guy is very high, and that's the special point for the silicon, that you have this Auger recombination that's also in there. So also we are actually the VOCs of the best heterojunction solar cells are already in the Auger limit. So the VOC, there is not much to do, but it's still non-radiative recombination. That's why it's so big if you compare it to the Shockley-Weiser limit. But there is not so silicon people next week can relax, so there's nothing. So now, who is doing CIGS? I can give you some advice. Now, okay, CIGS is also doing very well for thin film solar cells, so it's still ahead of the perovskites, still a little bit. There's a lot to do on radiative recombination, but there's also a lot to do on the JSC. Of course, we have this window. We have seen this in the quantum efficiency. There are a lot of losses with the window and buffer layer, so there's a lot of things to do here. Going to the perovskites, this green is smaller than that one, and that's already a lot. So it's even smaller, coming close to the crystalline silicon. But that's a very young technology, so that can be even smaller. And actually, if you compare different approaches of perovskites, so also can do it in the same way. You see that the technology is not very mature in the sense that everything is converging to the same thing. You have a lot of perovskite solar cells with very similar efficiencies, but some of them have that one very small and that one very large, and the other way around. So there is still a lot of development, and I think it's only a matter of time if perovskites catch up here to the other. So cadmium telluride, and then you can look at the other materials and see where is the most scope for improvement. And that's my summary. All of you got your working advice for next week, where you work on which device, what you have to do, make that smaller, and we have larger efficiencies, and I'm done. And we have a break. Thank you.
You want to ask a few questions now, or? Oh, no? No? Okay.
I have one quick question. Can I ask?
Yes.
So in the equation that you showed the correlation between EQE and JSC,
Yeah.
is it by assuming only there's one photon absorption, or we can have multiple photon absorption?
In principle, that Jean-François, he's not paying attention. You can do it. Just
is it included in this equation?
yeah, you can calculate your JSC of some real or assumed third generation device that makes two photons per 2 electron hole pairs per photons. You just put the EQE to 2. So that would be, I think the equation would be also could be used if you have more than one.
I mean, there's a linear relation between like EQE, I don't know, the lambda prime is EQE lambda 1 plus EQE lambda 2, a linear relation?
Not necessary. I mean, there's a lot of physics inside that. I mean, just formally, if you take that equation and say, okay, I mean, that's how it started, this consideration with the carrier multiplication. stuff that people just found out, okay, if I go to the double band gap energy and then switch my quantum efficiency to 2, just hypothetically, and then 3 times band gap energy to 3, and so on and so on, I can get much higher efficiencies. Nice. I mean, you can do it on, and for the JSE is also it's okay. The tricky thing comes on the J naught, so on the loss, because if you add this multiple carrier generation, that's another gain path. And by the principle of detailed balance, if you have a gain, you have also loss. So you have also to include the inverse of that very process in your calculation. And that gets somehow tricky on the J naught, but I'm sure Jean-François will on Friday give you the proper equation. No, not at all. No, but that's really, I don't know, yeah, there are certain approaches that are correct, but that not very appealing to read. So it's heavy stuff. But if you don't do that thing, you just getting out nonsense. I mean, then if you get the equation and do not include the losses, you can by equation build a solar cell that still has a photovoltage even if you switch off the light or something like that. So that's just not consistent.
Maybe we stop here. Thanks again, Uwe.